Okay, in this video we'll be going through the 2014 Level 3 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself, and once you're done or you get stuck, see how I go about getting the answer. Okay, question 1. This question is a bunch of information on how a organ works, like an instrument organ, not body organ. It's done using the sea, so with the waves and stuff. But the only part that we're interested in is this section right here, and it just wants us to calculate the length of the organ pipe. So a clue that we're given is this pipe is a closed-ended pipe, meaning it has a node on one end and an antinode on the other. We know that this means that the length is 1/4 of the wavelength, and because the wavelength is 2.6 meters, the length is just going to be 1/4 times 2.6, which gives us a length of 0.65 meters. Air is driven against a sharp lip, producing oscillations in the air, with a range of frequencies. Explain why not all frequencies produce standing waves in the pipe. So we know the wavelength of the standing wave forming in the pipe must allow for permanent places of constructive and destructive interference. Right, this makes sense because, if the places of destructive and constructive interference weren't permanent, it wouldn't be a standing wave, would it? Now, in terms of this pipe, the permanent place of constructive interference is going to be at this opening end because that is an antinode, and the permanent place of destructive interference is going to be at this end because that is a node. And again, we get this kind of shape of the wave. Okay, so these conditions need to be met. Now the sharp lip is going to generate a range of frequencies, and some of these frequencies are going to result in wavelengths that do match these conditions. And those are the wavelengths that are going to be produced. The range of frequencies that don't produce a wavelength that meet these conditions will not produce a standing wave. The C organ contains organ pipes of several different lengths. Explain why the differences in length of the organ pipe can affect the sounds that are heard. Right, we know that length is directly proportional to wavelength, and we know that wavelength is inversely proportional to frequency. I should probably make that look better. There we go. And so let's say that the length is increasing. This is going to result in the wavelength increasing, and therefore the frequency is going to decrease. And the inverse is obviously also true. If the length decreases, the wavelength is going to decrease, and the frequency will increase. So from this, you can see how the length directly affects the frequency, which is the pitch that we are hearing. And so you can write that in lovely words. The speed of sound in cold air is slower than in warm air. Calculate the difference between the third harmonic, which is the first overtone heard in summer, versus the third harmonic in winter. And the speed of sound in air in summer is 353 meters per second, and the speed of sound in air at winter is 330 meters per second. Okay, so if we are talking about the first overtone or the third harmonic, we know that length is 3/4 lambda. And so what that means in the diagram is that we're going to have a node over here, an antinode over here, a node over here, and an antinode over here. And as you can see, that's going to result in something that looks like this. Let's do that better. There we go. And as you can see, that is 3/4 of a wavelength, because if I finish that, the last quarter, you can see how there's going to be a node there. And so what we have drawn is 3/4 of a wavelength. And so because we know that the length is 3/4 of the wavelength, this therefore means that 4L all over 3 is equal to our lambda. Now we know from previous questions that our length is equal to 0.650 meters, and so therefore our wavelength is 4 times 0.65 all over 3, which gives us a wavelength of 0.867 meters. There we go. Now that we have our wavelength and we have our velocities at the different temperatures, we can find the frequencies of those different temperatures. Because we know that V is equal to F lambda, and therefore F is equal to V all over lambda, our F hot is going to be equal to the speed of sound in summer, which is 353, all over our wavelength, which we found was 0.867, and that gives a frequency of 407.31 hertz. Now, same thing for the cold, we get our F cold is equal to 330 all over 0.867, and that equals 380.77 hertz. Now, we're not quite done with this question, because if you look, it says calculate the difference between the two temperatures. So to calculate the difference, we take the larger number minus the smaller number. And so 407.31 minus 380.77, and that's equal to 26.54 hertz. There we go. The diagram shows a series of speakers connected together to a frequency generator producing a single frequency. The speakers act like a diffraction grating. The sound wave source is producing a note of wavelength 0.6 meters. The distance between the speakers and line AB is 35 meters. When a person walks along the line AB, the distance between two loud positions is 7.4 meters. Calculate the separation of the speakers, which is our D. So this is clearly a question of n lambda is equal to d sine theta. Now if we look at the information that we're given that the distance right here is 35 meters, so this is line AB, and this is our speakers. So you can see that that's that situation right there. So that's 35 meters. And along this line, the distance between two loud points is 7.4 meters. And so this creates a right angle triangle right here. And we can calculate this angle theta. We have our adjacent and our opposite side. So we can say that theta is equal to tan inverse 7.4 all over 35. And that gives us an angle of 11.94 degrees. So now that we have our angle, we're trying to find our D. In this scenario, we can just make n is equal to 1. And so we get lambda is equal to d sine theta, which is our 11.94. We know our lambda is given as 0.600 right here. 0.6 shall I say, not 0.600, that's not proper mathematical knowledge. And so we can rearrange as 0.60 times sine 11.94, and that's equal to our D, which gives us a value of 2.9 meters. There we go. Explain how the path difference of the waves causes positions of constructive and destructive interference along the line A and B. So this is our classic interference pattern explanation. When the path difference is a whole number of wavelengths, the waves arrive in phase. This results in constructive interference, thus producing a antinode, which is a loud spot. Now, when the path difference is a non-whole number of wavelengths, the waves arrive out of phase. This results in destructive interference, which produces a node, which is a quiet. Excuse the handwriting. Hopefully you heard what I said so you can write it in. Also, you see why I don't usually write my answers. I usually explain them. Also, I know you just wrote exactly what I wrote without actually thinking about the answer. And that is why I don't write explanations, because you just got to copy it and not learn. I know you did it. I know you did it. Also, if you write this, you're probably not going to get the mark. You had to explain it more in depth. This is just a general overview. So, joke's on you, mate. Explain the effect of the interference pattern on reducing the distance between the speakers. Okay, so if we take our equation, n lambda is equal to dx all over L. If we rearrange for x, we get x is equal to n lambda L all over D. And as you can see, x is inversely proportional to D. If D decreases, then x will increase. What this will result in is the loud spots, which are the spots of constructive interference, be further apart, meaning that there's going to be less of them, right? If we have our line AB, right, and let's say there were 5 spots of constructive interference. If they are more spread out, so this is now when they're more spread out, there's still going to be 5 spots. However, they're now going to be off the line A and B. And so effectively, the amount of loud spots has decreased. So essentially, the loud spots just get more and more spread out. And so on the screen, or the line A and B, there's going to be less fringes, or there's going to be less loud spots. Most students get this better if we talk about light. If we're talking about light, if these are now bright spots rather than loud spots of sound, we can imagine if those bright spots get further and further apart and we keep the screen size the same, so this line A and B now becomes like a blank screen, like a whiteboard. If they get further and further apart, the screen or the whiteboard remains the same size. So now if the light is more spread out, there's going to be less spots on the whiteboard itself because the ones that used to be there are now off to the side. And so this is essentially the same thing. The frequency generator is now set so several different frequencies are emitted by each speaker. Explain how the sound heard by someone walking along A and B will differ from that described in part B. Okay, so this question is kind of loaded and hard to conceptualize, but a very similar question shows up pretty much every year, except that question usually talks about white light. In white light contains all the visible frequencies, so that's anywhere from red to violet. And so if we put that through a diffraction grating, what we get is a bunch of different sources of different frequencies. This is essentially the same thing that's happening in this scenario. We have several different frequencies produced by each speaker, which each speaker we know is a source. And so several different frequencies from each source is the same thing that we have here. When we put white light through a diffraction grating, we essentially get several different frequencies out of multiple sources. And so the explanation is the same. We know that if we talk about white light through a diffraction grating, that central node, that n is equal to 0, is going to be pure white light because all the frequencies meet together. Same thing happening here. All the frequencies are going to meet at the n is equal to 0 node, and so all the notes will be heard at that location. We also know that when talking about white light, that central node is going to be white light. However, on the sides, we have red over here, and then violet over here, and then red over here. And so the same thing is going to happen with our speakers. We know that red light has the lowest frequency, and so the lowest frequencies are going to be heard at the edges, and the highest frequencies are going to be heard towards the middle. And we know this because n lambda is equal to d sine theta. So because n and d remain constant, this is just essentially lambda is directly proportional to sine theta. And if the frequency is large, therefore the angle must be large. And so there is the highest diffraction angle for the longer wavelengths. So now, just applying this to the speaker scenario, the lowest frequencies or the highest wavelengths are just going to be heard further apart from each other. And again, you can write that in lovely words. However, don't talk about white light and all that jazz. I was just using that as a cross-reference scenario. Don't talk about white light. Keep it towards the speakers. Okay, question 3. A tourist is watching a ferry boat coming towards her. The speed of the ferry is 5.5 meters per second. The ferry sounds its horn, producing a note of 95 hertz. The speed of sound in air over the water is 350 meters per second. Calculate the frequency of note heard by the tourist. Okay, so this is our simple Doppler, where we have f prime is equal to the frequency of our source times the velocity of the wave, all over the velocity of the wave minus the velocity of the source. Again, we know it's minus because this is on approach, and so we use our minus in this scenario. Okay, so now we can plug in our numbers. F prime is equal to the frequency of the source, which is 95 hertz, times the velocity of the wave, which is 350, all over 350 minus the speed of the ferry, which is 5.5 meters per second. And that gives us a observed frequency of 96.5 hertz. There we go. Explain why the sound heard by the tourist does not have the same pitch as the sound emitted by the horn. And if you remember, pitch is just another word for frequency, so why does it not have the same frequency? This is just a common Doppler explanation. Right, we have a ferry, which we can put as a dot, moving towards the tourist, right here. As it moves, we know it catches up to previously emitted wavefronts. And therefore we get our wavefronts looking like this. As you can see, the wavefronts in the front are bunched up, and therefore the wavelengths that the tourist observes is going to be shorter. And therefore, as velocity of the wave remains constant, so the speed of sound is constant, as v is equal to f lambda, as our observed wavelength has decreased, our observed frequency must increase. Now it's again important to note that the frequency has not actually increased, it's observed to be increased. Only the tourist hears the increase in frequency. The people on the ferry will still hear the true natural frequency, or the source frequency, I should say. Better terminology. And again, you know the drill, you can write that in lovely words. A second ferry, which is overtaking the first, also sounds its horn, producing a note of 90 Hz. For a few moments, both ferries are the same distance from the tourist, quite close together, and are both sounding their horns. The tourist hears beats. Calculate the frequency of beats heard by the tourist. Okay, so a common thing a lot of students do is they go 95 minus 90 and therefore the torus has 5 heartbeats. This is, I guess, intuitive at first glance, because that is the difference between the source frequencies of the varies. However, this is not the frequency that the torus has. Remember, the torus has the Doppler shift, so it's slightly higher. So what we need to do is we already have the frequency that the torus has due to the first vary, which is 96.5 Hertz. So now we need to find the frequency that the torus has from the second vary. And that's just our simple Doppler equation, where we have our source frequency, which is now 90 Hertz times 350 all over 350 minus 8.5, because now that is the velocity of the new vary. Let's probably draw that better. There we go. And this gives a frequency of 92.24 Hertz. And so now we have the two frequencies that the torus has. Now we can do the subtraction. So we get 96.5 minus 92.24, and we get 4.26 Hertz. There we go. Describe what beats are and explain how they are created. Okay, so beats occur when we have two waves that are close in frequency, which interfere at a fixed location. Because the frequencies are slightly different, there's going to be a slight difference in their phase, and therefore the phase difference will not remain constant. When they do interfere at that fixed point, there will be times where they go through constructive interference, which is going to result in a high amplitude and a loud sound, and there's going to be times when they go through destructive interference, producing a low amplitude and a soft sound. And due to them fluctuating between constructive and destructive interference constantly, this causes a sensation of beating. And so that's the theory, and you can write that in lovely words. And with that, we are done.